So what did we do last time? Okay, apart from that, of course you do it at your ease. What HAPs? And? Okay. Okay. What we'll do today is do some basic simple things on units. Okay. Well, we all the time do very basic things, nothing very hi-fi complicated things, but the simple things. Okay. See, it's very common you get to see the units in air pollution something like this. Okay. Okay, let's say here you will find this unit, you will find ppm, you may find micron per meter cube. You may also sometimes see as something very specifically written as like this. Okay. Sometimes you may also find something written as ppb. Okay. Sometimes also written as ppt. We also encounter units in air pollution as, okay. This is something very important that you need to recognize as, well, of course we can also express, okay, units in milligrams per liter also. No one stops, but generally in the air pollution, okay, air concentration or something, okay. If I ask you ppm, you all know ppm, okay, parts per million. Is ppm really a unit? It's not a unit, in fact. It's just a ratio, isn't it? But very frequently used, and in air pollution, when we talk about ppm, it is, unless specified otherwise, it is, we are referring it volume by volume. Okay. Okay. Ratio of volume of pollutant to the ratio of air, when the air is taken as 1 million volume of the air to the volume of the pollutant that is there. Okay. Let's talk about the water side. ppm in water. Okay. When you say ppm in water, what ratio are you talking about? It's a ratio, right? We all agree ppm is a ratio. What kind of ratio that we are talking about? Yeah, so ratio is it volume to volume ratio or is it mass to mass ratio? So remember that in air, water, we talk the ratio, it is generally called weight white ways, right? Okay. You also have in water, on the water side, milligrams per liter will be equal to ppm, right? We all know that. Why? Density of water is 1000 watt, kilogram per meter cube, okay? And because of that density is 1000 kilogram per meter cube, this relationship holds good, okay? All right. If I go with something similar, can I also say for the water or for the air, the ppm will be equal to milligrams per liter? No. So here, what we say here is not equal to ppm. Okay. And suppose will it be true even for the seawater that ppm will be equal to milligrams per liter? It will not be, because the density of the seawater is not 1000 kg per meter cube or 1 gram per cc or whatever. Okay. So milligram per liter is not equal to ppm. And the other thing here, what you see is this meter cube. Okay. It can be very tricky. Okay. We don't want to say meter cube just because the meter cube in air and meter cube in water is a lot of difference. Okay. Meter cube of air and meter cube of water can be very, very different. Why? Well, look, the volume is the same, but this volume, okay, where the 1 liter of water will be always by and large will be seen as a 1 liter, but the meter cube of air, little change in the pressure and temperature, the volume will change. So normally, okay, normally, can I do something here that so that we don't, okay. So the other thing you need to remember really is specify pressure and temperature with volume. Okay, that's what we need to do. So generally it is a matter of practice. If it is a convention. Just say meter cube, okay? Because otherwise every time we have to write. So most of the time the standard things are translated to these conditions, the temperature, so that when you express something, either you write the actual temperature and pressure at which the volume is measured, or you convert that to the 25 degrees Celsius and 1 atmospheric pressure and just simply say meter cube. Okay. All right. Okay. So we'll go back to the air thing, and what we want to do in the process, derive a relation between this and ppm. Okay. Question for you: is the ppm concentration in ppm, does it, when I'm expressing the concentration in ppm, do I need to specify the volume, do I need to specify the temperature and pressure, or I don't need to specify? No. We don't have to specify. So we have the advantage in the ppm when we are expressing in ppm that we don't need to specify the pressure and temperature, because it is simply the ratio. The same pressure and temperature is applicable for the pollutant as well as for the air in which it is dispersed. Okay, so that is the advantage ppm have. But with the microgram per meter cube is, we are very familiar to understand the terminology mass per unit volume. So we need to derive some expression which is in 1 ppm, and I'll try to do that. Okay, so starting from here, 1 ppm equals to, okay, and in air we say ppm is volume to volume ratio. Okay, so then I said, okay, should I say what, 1 liter for example, okay, of the pollutant, some gas, okay, whatever that gas may be, divided by how much volume of air? I just want to say 1 ppm is really in true sense what it is. 1 liter of pollutant, I'm specifying the units as liter. So I've taken 1 liter of pollutant gas, which is dispersed in how much? 10 to the power 6. In fact, we take 10 to the power 6 plus 1, right? That is the total volume that is expressed. But we'll ignore that one. And then, okay, fine. Okay. Basic thing. We have just written what we know. Okay, and now just remember where I have to go from ppm. I have to go to microgram per meter cube. Okay, so what I need to change? I must change this liter somehow into mass units, because from this liter I want to reach to microgram. Okay, so how can I do that? Because this is already air, that is also air. So this I can also say this one if you like. This is 1 liter by can I say that? Right, fair enough. Okay. Now let's see about the pollutant. So more or less I got the meter cube down there. I must change the liter into the mass units. So if you recall your at normal temperature pressure, the volume occupied by 1 mole of the gases will be how much? You recall that Avogadro's principle? So we know that 22 point, I'm just doing from very basic things, liter of gas, okay, will be equal to how much molecular weight of the gas? 1 mole of the gas. Okay. So that 1 mole will be what? Nothing but 1 times molecular weight. And what is the units of this one? The molecular weight here? Grams. Okay. In grams. We all know that, but we will still write that as grams. Okay. Job is done. Okay. So 1 liter of the gas or the pollutant that we are saying will be equal to how much? Molecular weight. Don't forget that will be in grams by 22.4 liters. Achha. At what conditions? Let's not forget. At what temperature? Standard. 273 Kelvin, 1 atmospheric pressure. Okay, let's not forget. Let's go and replace this thing there. So 1 ppm equals to molecular weight, okay, which is in grams, don't forget, divided by 22.4, correct? You will point out if I make a mistake, okay, times fine, okay. What do I want to get in micrograms? Okay, let's change this to micrograms. So this should be equal to become 10 to the power 6 grams to micrograms, molecular weight, divided by 44.64, is it? Anything else? Nothing, I guess, right? That's all? You've taken care of everything. Divide by 24 to 2 or 3. Okay, fine. Don't forget that meter cube are still at 0 degrees, right? Or 273 Kelvin. And 1 atmospheric pressure. But it's a good idea to express more at 25 degrees Celsius or something. Okay, so we just simply change the volume at the thing what we need to find out. Okay. Pressure, I am assuming pressure to be the same. Pressure changes I am not incorporating, both are at 1 atmospheric pressure. So that goes off, and I want to find out the volume at this temperature. Okay. So suppose this, what is this volume right now at the conditions whatever per meter cube, so 1 meter cube. Okay. So 1. What was the temperature here? 273, correct? Okay, 273. V2 that I need to find out, okay, divided by 298 at 25 degrees Celsius. So please tell me the value of V2. 1.09. Alright, so what do I do here? To get the conditions at temperature like 298 Kelvin or 25 degrees Celsius, what I need to do is 1 ppm equals to 44.64 times the molecular weight divided by what? Because my new volume is not 1, but it is 1.09. Okay. Please give the number. 40.95. 40.95 or 41. We will write 40.95, but you can always. And I don't have to specify the pressure temperature because we have said when it is 25 degrees centigrade. Okay, we are not saying this one. So what we have done in this little 10-15 minutes from very basic principles we have derived a relationship in the atmosphere for the gaseous pollutants. When the concentration is given in ppm, you can convert this into the microgram per meter cube and back and forth. We should not forget to write here. Here the box is complete. Okay. This is fine for the gaseous pollutants, but for the particulates or dust, we don't have any such relationship. Why don't we have such a relationship? Because you see, we don't know the density of the particles. You know, it will be a mixture of the particles, and once we don't know the density, we can't change. So always remember the gases. Okay, whatever that gas may be, or in the vapor form, we can always express in ppm or in microgram per meter cube, but particulates or dust levels are always expressed in microgram per meter cube or milligram per meter cube or mass per unit volume. Okay, whereas for the gases we can express in ppm or ppb or ppt and things like that. Okay, simple thing. Okay, little assignment that you need to try. Okay, get the same relationship, okay, from the universal gas law. Okay. I will not use this thing in deriving this thing, okay, but you need to use this, the gas law, which we all understand, study from class 9th and 10th, and we need to get to the same thing. Okay, this you try and make sure that you are able to do this. Okay. Is there anything else which I want to talk about? Okay, maybe a small thing. Ambient air. Okay. Normally we express the units here something like milligram normal meter cube. Here this normally nearly is taken as n means that is the temperature, pressure is 1 atmospheric. You may find sometimes also like this. A stands for actual. So whatever the actual pressure and temperature which might be specified somewhere in the description, that might be the actual pressure and actual pressure and temperature. It's also not uncommon to define this in ppm at the source. Okay. Sometimes some people also like to express a different system which is of different kind, that is the emission rate, emission quantity, so much kgs per day. But here mostly in ambient air we write the units generally in micrometer cube, microgram per meter cube, because the concentrations are low. So we also write, it will not be a very good idea to write concentration in milligram per meter cube in ambient air. That number will look 0.000001. Okay, that sounds very funny. And similarly here we use ppm, but many times we use ppb because the concentrations are low. Okay, so don't be surprised like if you know that things are interchanged at ambient air and things like that. Sometimes when the pollution level is very low, we also like to express in nanograms. And remember, if this is not at 25 degrees Celsius, we will have to specify the pressure and temperature that we are talking about, because these are the very little fundamental things, but many people at many levels make such kind of mistake. Okay. Okay, this is another assignment number 3. Read the question. Okay, and you should do it. You should try it at your room or home or something like this. Let me see if everything is okay here. A power plant of 500 megawatt capacity burns 20 ton of coal per megawatt per day. Fine. During the burning process, the plant has the following information. Okay, the sulfur content in the coal is 0.5%, and then it is clearly specified weight what weighs. In the coal, composition is normally given in weight by weight basis. Okay, pressure in the stack will be slightly higher than the pressure that you encounter in the ambient air, that is 1.1. The stack exit velocity, the velocity through which the gases are coming out, is 15 meters per second. The diameter of the stack, so very big stack, 10 meters, huge diameter. Okay, a little bit more than normally it is provided. Okay, it's about 10 meters. Now you have to estimate SO2 emission in kg per day, in ppm, in milligrams per normal meter cube. Okay, just read this the same. There is no difference between this and this. Okay, assume complete combustion of sulfur compounds. Okay, there is another additional thing which is given. If the hydrogen content of the coal was 10%, again weight wide base, because the coal will have both carbon and hydrogen. Calculate the concentration in milligram meter cube also on dry basis. Okay, so this you should try this one out. Why, question you might ask it, what is so big thing to dry basis? Why dry basis? Why? Generally preferred things to do on dry basis. The reason for the dry basis is when we are really expressing the concentration. So you have the milligram per meter cube, which this meter cube is from the exhaust or the process or combustion. Process exhaust plus water or moisture. And you see, this may, normally these things are fine, but this may really vary from coal to coal. And generally to standardize the things for the comparison purposes, we put it onto the dry basis. So what you will do here when you want to finding out this concentration, you will take the volume of the air that is going out will be the total volume that is going out minus the volume of the vapors that will go out. So that you can, some calculations are done here, but I would like that you try it yourself. Okay, there might be some mistake as well here, but then if I have the 1 kg of sulfur, let's say, how much will be the sulfur dioxide that will emit? Suppose I have the in coal, okay, I burnt a coal which has 1 kg of sulfur, okay, how much will be the sulfur dioxide if all sulfur is converted to sulfur dioxide? Whatever, just do it quickly.
So 1 kg means 1 kg.
1 kg of sulfur is there that got burnt, and how much will 2. Why I want you to do is always remember the sulfur to sulfur dioxide will always be doubled in quantity. A simple thing to remember. And many times sulfur dioxide is many times talked about. It's such a common pollutant. They say, all right, we have this sulfur so much, like then you quickly know how much is the SO2 you're talking about, because the factor is very simple, just multiplied by 2. Okay, that was the idea of just asking you that thing. Okay, now what do we do? The next thing, this one, you do it yourself. I mean, like this thing. Yeah, that's fine. I mean, this because you write down, you can have a look also onto this thing, but I really want you to try it out yourself, so that you are a little bit practiced into the unit conversion and things like that. Because this is important in air pollution, because many times people mess up, like small things, and can talk the big things, but we always wish that small things are not. We don't make mistake on small things. And this is typically, all numbers are typically true for about 500 megawatt plant. Okay, so you are really, the numbers you will get will be very realistic as to what you will find really in the stack and things like that. Okay, go further. Okay, now we are talking about we are entering into a new topic, and that will be, we are talking about particulate matter, and briefly write as PM. Okay, so some definitions. Okay, the TSPM is, or in fact many people just simply call it TSP. Okay, in US literature you will find it as a TSP. TSP is the total suspended particulate matter. Well, all particles smaller than 50 micron meter are called TSPM. And as I gave you the feel, how big is 50 micron is the size of your hair. Okay, diameter of the hair, if it's the same. So that is called this thing. There is another terminology called PM10. Okay, it is not written quite the way it is written here, but this write PM subscript 10. Okay, all particles of size less than 10 micron meter, and they also call it the inhalable particles, again related to the lung functions and things like that. And then you have the PM 2.5. Then they are called all particles with less than or equal to 2.5 micron meter. It's called respirable particles or fine particles. Two names. Okay, and most common is the fine particles. Okay, and particles PM 0.1 or 0.1 less than or equal to diameter 0.1, we call the ultra fine particles, and they are really very, very fine particles. Okay, there is another terminology. Okay, that is written as PM test 10-2.5. It means the particles of size less than 10 micrometer but bigger than 2.5, 2.5 or bigger. Okay, so that is what they call the coarse particles. Having said the diameter, specified the diameter, let me also tell you this diameter is not the ordinary diameter. Okay, and this is something, the diameter, which all the time the word diameter you see in the slide, and what I am speaking really is a diameter called aerodynamic diameter, and we will see what this is in a moment. I think you correct this. Better to say it's coarse fraction. We want to discuss this. Okay. Want to discuss this. And I use the word aerodynamic diameter. See, the funny thing here is that particles emitted from air pollution sources and formed by the natural processes have a number of different shapes and densities as indicated in figure 1. See here, how do you define the diameter of these, or this for that matter? Okay, and if it is a hollow, okay, this might behave very differently in the atmosphere as opposed to a flake, okay, or a fiber, okay, or the condensation flock or the aggregate, which you may not be able to see as fine as this one. Okay, so we must standardize the whole thing to a particular thing, okay, and that's what is the aerodynamic diameter is, standardizing the things, okay, so that they will behave little they behave in a certain fashion if we can define the aerodynamic diameter, because depending on the aerodynamics. It will be a little interesting for you to note that some of the fibers, okay, asbestos for example, asbestos is, since we are talking about the units, asbestos is not measured in terms of microgram per meter cube or ppm or this thing. Asbestos is in air is always measured as number of fibers per meter cube. Okay, that's little interesting. So we want to define something very standard, okay, rather than like going by this one. Just look, this is the real picture taken from a site, okay, and you see the particles can be, there can be holes in filter, and you see the particles size can vary and things like that. So we need to, it's nothing very circular, that kind of thing. So we need to define the aerodynamic diameter. Okay, this is a little description that you see here. But I think quickly let's go through this. This is a very meaningful thing. That's what is the purposely defining the particle size for spherical particles is easy, fine. It is simply the diameter of the particles. For non-spherical particles, the term diameter does not appear to be strictly applicable. For example, what is the diameter of a flake or a material or a fiber? Also, particles of identical shapes. Okay, see the interesting thing. Also, the particles of identical shape can be composed of quite different chemical compounds and therefore have different densities. Okay, the difference in the shape and density could introduce considerable confusion in defining the particle size. Okay, because the behavior of the particle will be different. We are defining the diameter more because of the behavior of the particles. In air pollution control, it is necessary to use a particle size definition that directly relates to how the particles behave in the fluid such as air. Okay, so that is basically what we are trying to do. We are trying to standardize and normalize the thing, like, so there is no confusion as to the things. The term aerodynamic diameter has been developed by aerosol physicists in order to provide a simple means of categorizing the sizes of the particles having different shapes and densities with a single dimension. Okay, the aerodynamic diameter is just see what is the aerodynamic diameter. The aerodynamic diameter is the diameter of a spherical particle having a density 1 gram per centimeter cube that has the same inertial properties like the terminal settling velocity. Okay, the diameter of a sphere particle having the density of 1 gram sphere that has the same inertial properties, that is the terminal settling velocity. So if I have another particle and its density, if I have the density is 1 gram per meter cube, and then it is having the same velocity as my standard particle, then it will have the aerodynamic diameter of whatever that the real spherical diameter. Okay, I'll explain you a little bit in a moment. The velocity of a falling particle when the gravitational force is downward is balanced by the air resistance or drag or force upward on it. It is determined by the Stokes Law. You all remember the Stokes Law from this thing, and you can also say that Stokes Law is the balance of three forces: drag, buoyancy, and the gravity. Very good. Okay, and that is the time when all three forces are balanced. The particle will move with a constant velocity. That's called the terminal velocity. And the aerodynamic diameter of all particles greater than 0.5 micron can be approximated using the following equation that comes. Refer to aerosol textbooks to determine the aerosol diameter of the particle less than 0.1. This is a little more complicated. Okay, I think maybe I need to explain something quickly. It's hypothetical. Suppose I have the standard balls. What balls I am referring to is density is 1 gram per centimeter cube, and diameter is, let's say, diameter, I'm not giving you any units, but let's say diameter is 1, whatever the unit may be. Okay, I may have the same property, same thing. Okay, I may have another ball, same properties. Okay, it'll have some terminal velocity in the air, right? Okay, so suppose that velocity is, or let's say terminal velocity is Vt1 here. The density is the same, dia is 2, and velocity is Vt2, and so on and so forth. Okay, correct? Okay. Now this is the standard thing which probably don't even exist. Okay, but I'll take my actual particle. I can take my actual particle. Okay, and then I can have, I will see that particle, if that particle had the velocity, the density. Now this is actual. Suppose I could see that how things will change for the particle. The density is 1 microgram per meter cube. That is fine. So it will give me some terminal velocity for this my actual particle. Then I can compare where this actual particle, terminal velocity is matching out of this one. So this diameter of my actual particle may look like it's, let's say, 3. Okay, I'm not giving the units. Okay, but I have to see what is its the terminal velocity and compare with this thing. Okay, okay, and then that will be my actual aerodynamic diameter. So in fact, a diameter which looks to you 3 micron meter, which you measure by some means, whatever, but that aerodynamic diameter may be more or less. Okay, so I think there's a next sheet that probably explains a little bit more. So normally people use this expression, but the other methods also. So to find out the aerodynamic the particle diameter, you find out the Stokes diameter. Okay, how can you find out the Stokes diameter? How will you find the Stokes diameter? Let's say the particle density affects the motion of the particle through a fluid and is taken into the account in equation. The Stokes diameter of the particle, listen carefully, is the diameter of the sphere that has the same density and settling velocity as the particle. Stokes diameter of a particle is the diameter of a sphere. From where? From the standard thing. Okay. You are comparing with the standard, which has what? Based on the aerodynamic caused by the difference in the Stokes diameter of the particle is the diameter of the sphere that has the same density and the settling velocity as the particle. Okay, it is based on the aerodynamic drag force caused by the difference in velocity of the particle and surrounding fluid. For smooth spherical particles, the Stokes diameter is identical to the physical or actual diameter. Okay, so you can find out the Stokes diameter, and then you have the density of the particle. This is more like, this is obviously, you can see this is an empirical expression. This is not that one. So if you know the Stokes diameter of the particle and the density of the particle, then you can find out. Okay, how do you find the Stokes diameter? Yes, use that expression. Okay, yes, okay. So now what we will do is that we know the terminal velocity of the particle, we are measuring the terminal velocity, and for that one we are finding the diameter from the Stokes law. Normally we do the reverse thing, we assume the diameter of the particle and find out the terminal velocity, but what you are measuring is terminal velocity you are measuring, and based on that expression of the terminal velocity you are finding the diameter of the particle. Ulta kaam ho raha hai. Okay, it's in reverse direction that you're going on, and that is the Stokes diameter that you can find out, and the density of the particle is known, and that's how you can find out the aerodynamic diameter of the particles. Okay, this little thing as how things, actual diameter, aerodynamic diameters can vary. Okay, this is solid sphere. Okay, all these things had the diameter as you will probably measure normally is the 2 micron meter. Okay, good. See here, what this slide is trying to tell you is that, well, you have the particles different this thing, and then you have the different diameter, as you will see, 1.4, 2.8 and 1.3, but their densities are varying. Okay, but they all are equivalent to 2 micron meter in the aerodynamic sense. Okay, so that's what I was trying to say. Well, you can really be, I mean, if you don't know the densities and things like that, you know, like it's these are not the real thing that we want to use in air pollution engineering or air pollution control. So these are this thing with different densities. You might get the equivalent aerodynamic diameter could be the same. See, all three look very different, but they will behave in the same way in the fluid air. Okay, and here what you see here is that you have the same size here. Okay, and the density is varying, and the equivalent aerodynamic diameter, see, in this case it is fine, because why? This is 2 here and this is 1 here, so you get 2 here, and here because the density is different, okay, the diameter is different. Although you will measure with whatever ways and means you have as 2 micron meter, but we would prefer this to be called as 2.8 micrometer size of the particle. Okay, same, you might measure this as 2 micrometer, okay, and then we might say, well, this is little not quite correct in the sense we want to use it, and we might say that this is actually 3.5 micrometer. Okay? Okay. A little ordinary example for you to have a look onto this one. Suppose you are given, calculate the diameter aerodynamic of the particle having a Stokes diameter or DPS, that you can find out, as I said, is 2 micron meters and a density of 2.5 gram per centimeter cube. Find out the aerodynamic diameter of the particle, and you will see here what is the density is what is high. If the density is high, the aerodynamic diameter will also be higher than its normal diameter as we see. Is that correct? Yes. You started with something like 2 micron meter, and then you end up with the aerodynamic diameter of the 3.29. Okay. Okay. Some more information on the particle size with respect to their sources. Okay, and what they come out this thing. See, interesting part is that we also call it ultra fine. Okay. Well, unfortunately, some definitions are a little variable, but these particles are this 10 to 100 microns are really, and they come in the large range, people call it. So you will see the fly ash. Okay, because that's you will encounter very many times. It is both, part of it will be in PM10, okay, and part of this will be in the bigger than 10 micron here, you see here. Okay. The coal that we fire in the power plant, what do you think will be the size of the coal that we fire in the power plant, in large power plants? Well, we don't know, but then it can be anywhere from like 20 micron meter to 50 micron meter, that's right, because it's pulverized, okay, it's pulverized. But you see, when the fly ash that comes out, that is much finer than the things which you fire. So, because no, interesting thing is, no mechanical processing can get you the below 10 micron meter, okay, no matter how much you crush it, okay, you can't go below 10, below 20, 30 micron meter. But then once you fire it, then it can, the fly ash is in the lower side. Carbon black that you see from the exhaust coming out, that can be of this side. Paint pigments can be this side. Pollens can be that, you know, the pollens in the air because of that, the plant thing which is flies off here and there, this can be larger thing. Tobacco smoke, we all know about the tobacco smoke. Cement dust, again, some portion goes into this side, but still it will be largely this thing. Because cement is again not quite a simply mechanical process. What happens in the cement? Why you see you have the crushing of your limestone and things like that. First the mechanical crushing as much as you can do, and then what we do? If you recall, we do the calcination, drive out the carbon dioxide component through that one, right? That's what is the normal cement making. So CO2 is driven out, okay, and then as a result the size of the particles will become smaller, right? So you start with large particles, but some particles will become small. Milled flour, okay, but I really doubt that if they can go at 10. Coal dust, again it doesn't go below 10. Oil smoke is really very fine particles. Metallurgical dust and fumes, well, that can. And the photochemical smoke, what you see in the air, okay, that can be again defined. And dust, etc., etc. Okay, dust is more like insecticide dust, but dust is more like a normal terminology. Okay, unfortunately there were more things to talk, but before we end, I want to leave you with some interesting thoughts or interesting point. Well, I don't want to ask you this question, but maybe I'll just ask. Tell me if you want to tell me. If you don't want to tell me, don't tell me. Who smokes? No one smokes. Okay, very good. Okay. See, this is something from the last class that I want to talk to you. This is cigarette. All cigarette comes with filter, except the Charminar cigarette. And some people who are fan of Charminar, they give a damn if the filter is there or not. Okay. And this is what is a little fiery portion here. Okay. And you will see little trickle. Okay. And this is a little which is like fire on the tip. Okay. What it signifies in the sense that what we did in the last class. Source, but formation of secondary pollutants. See here, when you really, you lit up the cigarette and you will find there is nothing. There will always be a gap, and the fumes you will see or the particles you will see will be at a little higher level. You know, as these vapors, okay, which are in the vapor phase, okay, and they will convert into the particulates or the smoke that you see here. And you will not see any smoke that is here. You will see the smoke here. So started with the gaseous pollutants, it might condense, it might nucleate, it might agglomerate, and then you see a lot of smoke here. So this is basically going from primary to secondary, and it is both the phase conversion as well as becoming from the gaseous to the particle. You will not find anything here, but you will find a lot of smoke here. Okay, And this is what is the again conversion of this one. I was this is the time I was sitting at the airport waiting for the planes, my flight to come, and then I could see at the runway, the planes are coming, and like they land and then they're taking off and things like that. Every time, like because it was a big screen, I could see that every time the plane was landing, as soon as they will hit the wheels or the tires will hit to this thing, there used to be smoke, there used to be dust, and I always used to think that it's the dust that is coming out. And I said, well, maybe the runway is dirty and things like that. There's some dust which is there on the road that goes out. But that is not the dust. It is the heat. The tires, as they hit to the ground and the brakes are applied, it is the tires, the high temperature, the volatile components or this thing that comes out, and it goes a little up, and then you see the smoke. And you will not see the smoke at the runway. And you go a little up, and then there's a smoke. There's a puff of smoke that is going out. So again, that is some kind of secondary particles are formed, and that's how the volatile components of the tire, it slowly goes off from there. And it's because of the heat, it hits to the ground, and then as it, suppose these are the tires, as it hits to the runway, and you will see the smoke, not here, smoke, like with some gap, which was very clearly that could be seen. And then I remembered this example, and I said, well, this is not the dust on the runway that is causing the smoke or something. And it is not very small. Like I must be something like maybe 400 meters, 300 meters, and I could clearly see that smoke coming out. Like the organics or the volatile compounds which are part of the tire, and that goes in this thing. And this is still a matter of investigation, and people do a lot of studies, and then they're trying to see, well, this is the non-exhaust emissions. People talk about this. Maybe we'll have the time, we'll talk about that. Just this is a small thing. Observe the cigarette if you can observe, and you will see that this is what is happening. And then you'll find a gap here. Okay, we'll stop here.